Okay, so I'm Serina, as introduced. I'm currently a postdoc at Microsoft Research in New York City, starting next year as an assistant professor in computer science, joint appointed with computational precision health at Berkeley. So today I'm going to be presenting about inferring and simulating human behaviors with machine learning. Can everyone hear me right now, including those online? Okay, great. So to begin, human behaviors are crucial to understand for high-stakes decisions, but often difficult to observe. What do I mean by that? For example, in pandemics, we care a lot about contact networks. Diseases like COVID spread through contact networks between people. They guide how we reopen, how we lock down, how we distribute vaccines, and so on. But it's often hard to know who exactly is coming into contact with whom. As two other examples, masking and vaccines, these are very important behaviors to understand during public health crises like pandemics, but it's often hard to know exactly who is doing what. And here are some reasons why behaviors can be difficult to observe. I'm sure you've encountered these in your own research. First of all, behaviors can be highly heterogeneous. And so, for example, during pandemics, people's rates of social distancing or vaccines, that can differ across, say, socioeconomic groups or political affiliations. And so we need to observe behaviors at fine enough granularities such that we can capture this heterogeneity. Second, behaviors can change rapidly over time. Again, during pandemics, people rapidly decrease their mobility early in the pandemic. And so you need data that can capture these changes over time, ideally in real time if you're a decision maker. Another issue is costs. Surveys cost money. They cost effort to conduct. That often limits how large of a sample size you can collect and also how frequently you can do that survey. And so that affects the survey's ability to capture these first two attributes, heterogeneity and rapid changes over time. And surveys can also be prone to self-reporting biases, especially for sensitive things such as vaccine uptake. And another issue is privacy. Even if you could collect all of this data on human behavior, you might not necessarily want to release it. And then finally, sometimes behaviors can't be observed because they literally haven't happened yet. Maybe because they're future behaviors or because they're counterfactual behaviors, so they are not observable. And so in all of these cases, I take two approaches to dealing with this challenge of observing behavior. First of all, inferring behaviors from novel data sources, which I'll explain what those are. And second, more recently, simulating behaviors with large language models, taking advantage of their recent capabilities to simulate realistic human interactions and responses. So on this point of novel data sources, they have a couple of characteristics that make them really ideal for addressing these challenges. First of all, novel data sources like search logs or geolocation data from cell phones, they cover a wide swath of the population, and they have pretty good penetration across many countries. And so that allows you to capture these heterogeneous behaviors with such a large sample size that you can then slice it and dice it and get all of that heterogeneity. Another thing is that they tend to be high frequency, right? So for example, pings from your cell phone, those are going off all the time. So you can capture these changes over time, often with real-time reporting. And another thing is that these novel data sources are collecting your data passively. And so instead of you having to generate that data every time, it's passively getting collected. That gets around survey costs, as well as can help with avoiding these self-reporting biases. So a bunch of these advantages to novel data sources. But recently, I've also been really interested in simulations as a complementary method. And simulations can help with all of these challenges. And in particular, I think they can help you in three places where novel data sources might not be able to. The thing about costs is now you can actually carry out maybe the same survey questions with synthetic respondents, and this can help you greatly reduce costs with pilot studies, for example. When privacy is an issue, simulations can help you get realistic synthetic behaviors while still protecting the privacy of real individuals. And then finally, simulations can help you understand future or counterfactual behaviors across a wide variety of scenarios. So there's all of these exciting opportunities. Of course, an open challenge is how do we validate these simulations and see whether they produce realistic human behaviors? And that's one area that I'm quite focused on right now, validation and usability. And finally, I'm not just interested in behaviors for themselves. I'm interested in modeling them in the context of these decisions that I introduced at the beginning. For example, a lot of my past work is based on public health. And so thinking about decisions like reopening or vaccination, and then taking these estimated behaviors and modeling, for example, disease outcomes over those behaviors, or thinking about competing objectives during decision making based on those behaviors. So that's an intro. Today, I'm going to be trying to cover both of these approaches. In part one, we're going to talk about inferring behaviors from novel data sources, focusing mainly on work where we inferred mobility networks from geolocation data and then modeled COVID over those networks. But I'll also touch briefly on other types of data that I worked with, like speeches or search logs. And in the second half, I'll talk about simulating behaviors with LLMs. I'll focus mainly on a recent paper where we generate social networks with LLMs, but then we also have some ongoing work that I'd love to touch on. That's about simulating public opinions or creating user simulations for better AI evaluation. That's something I'm working on right now at Microsoft. So to begin, let's talk about mobility networks. This is a paper that was published in Nature, which I co-led with Emma Pearson and Peng-Wei Ko. So as I said earlier, understanding this contact network is quite crucial. It can help you guide, for example, how do we reopen safely based on who is coming into contact where at what kinds of places. And it can also help to guide how do we reduce disparities because people have varying levels of contact in different places that can help you guide which sort of communities are more at risk and how do we reduce those disparities. The challenge, of course, is we don't always know the true contact network between individuals. We don't quite track who is coming into contact with whom. And so in this situation, what can we do instead? Well, prior work has tried to get around this in various ways. For example, maybe you can assume the graph structure. You assume something like uniform mixing within cities. Or you could try to model contact at a much coarser granularity, like airline networks, where you actually do have the data. But both of these approaches miss this important heterogeneity that we just discussed at local levels. People don't mix uniformly within cities. Another option is to add many parameters to an epidemiological model to make up for the fact that you're missing this contact network. So maybe you have transmission rates for every neighborhood. But the challenge with that approach is that the data to fit these kinds of models is very scarce. And so models with many parameters tend to overfit on the available data, and they have trouble with generalization and identifiability. And so our solution instead is to infer fine-grained mobility networks directly from aggregated location data and use those mobility networks as proxies for contact. And our premise was this. If you can successfully infer these complex fine-grained networks from data, then your model can actually be very simple. The networks will basically absorb much of the complexity of disease spread so that you no longer need so many parameters, but you can still accurately model the spread of disease. More specifically, this is a network inference problem that we have. Ideally, we want the hourly visits of people to places so that we can model the spread of infection based on who is visiting where at the same time, in the same hour. However, most location data doesn't provide such fine-grained networks. At best, they provide aggregated visits over people and places. So for example, we use SafeGraph data in our work. Maybe you're familiar. SafeGraph data is aggregated to the level of census block groups, or what I'll call CBGs in this talk. So they're local neighborhoods of around 600 to 3,000 people. And then SafeGraph also provides visit counts for individual points of interest, or POIs. And those are public locations such as restaurants or grocery stores. And so SafeGraph actually has the individual GPS pings from people's cell phones, but they aggregate the data in this way in order to preserve privacy. And so given this data, we want to keep it aggregated, but we want to reconcile the total visits, the total hourly visits at CBGs and the total hourly visits at POIs, so we actually have the full network of visits from CBGs to POIs. And specifically, we're trying to infer this bipartite network that says, in every hour, how many people from each CBG visited each POI. So what exactly does SafeGraph provide? Well, as I mentioned before, we have the hourly number of visitors to each POI. And then we also have the hourly number of people from each CBG who are out and about and visiting some POI, but we don't know which one. And then we also have a monthly estimate from SafeGraph of where the POI's visitors are coming from in terms of their home CBGs. So you can see that this gives us the network that we want, but it's at a monthly instead of an hourly granularity. The question is, how do we reconcile these pieces of information? Our key insight is that we can use this algorithm called iterative proportional fitting, or IPF, to reconcile these two data sources and infer hourly CBG POI networks. And to take a step back, I'll provide some background on IPF. You might know it by other names, such as Stinkhorn's algorithm, or biproportional fitting, or raking, as it's commonly called. IPF takes as input an initial matrix, and then target row marginals P, that's what you want your rows to sum up to, and then target column marginals Q, that's what you want your columns to sum up to. And IPF tries to solve the matrix balancing problem, which is basically to come up with two diagonal matrices, D0 and D1, such that if you scale X by D0 and D1, you are now matching both the target row marginals P and also the target marginals Q. And IPF does this by basically iteratively scaling the rows and then the columns of the matrix. I'll show you what I mean. So on even iterations, we're going to scale the rows of the matrix by adjusting D0, so that now you're able to match P, the row marginals. And then on odd iterations, you now adjust D1 so that you perfectly match the column marginals Q. And you're using the latest version of D0 as you're iterating on D1. And you go back and forth, adjusting D0, adjusting D1, adjusting D0, and so on, until hopefully you converge. And I'll talk about convergence conditions if people are interested. But it's known that if these iterations converge, the fitted matrix that you find is going to match both the target marginals P and the column marginals Q at the same time. But not only that, there's a very nice interpretation, which is that it also minimizes the distance to the initial matrix in terms of minimizing the Kullback-Leibler or KL divergence. And so our idea is to use IPF to infer these hourly CDG POI networks. We have the hourly visitors from the CDGs into the POIs. Those serve very naturally as your target marginals, P and Q. And then you can treat the monthly network as an initial matrix. And then using IPF, we can infer hourly CDG POI networks, where now the hourly networks do satisfy the marginals that you're given, but are otherwise as similar as possible in terms of minimizing KL divergence to the monthly network. And since there's some rich methods here, we actually wrote a second paper about this at ICML, co-led with Fred Kohler and Jianan Chu, where we really thought about what are we doing here when we use IPF to infer this dynamic network. The first thing that we observed in this paper is that the problem that I just described with safe graph data is actually a more general one. And so this will appear wherever you're trying to infer a dynamic network where you have its time-varying marginals, but you only have its time-aggregated network. And so beyond mobility, this problem could appear across domains, where it's easier to observe the marginals than the interiors of the network. For example, think about transportation. Maybe you have a subway system, and it's easier to observe the swipes into and out of stations based on turnstile data, but it's hard to know the paths that people are taking between stations. Another example might be migration. Easier to observe inflow and outflow out of regions, but hard to know where people are moving from or to. Yes. Yeah.
Could you use something like this to infer what career transitions people were making? Like you see how many people there are in every occupation, and that moves over time, but you don't get to see that.
I think so. I mean, you would need some sort of time aggregated version. Are there good? So like basically the idea is you have some maybe once in a while you do a survey for people, and then they do answer the question.
Counts, but the sort of like how people flow between occupations is somewhat mysterious.
Yeah, I think you could do that as long as you also have the time aggregated network as well. Yeah, so we could talk more about that.
That initial matrix.
You need the initial matrix somehow, yeah. So if that exists, then you can try to get a more temporally granular version.
Profiles.
Yeah, LinkedIn profile. Yeah. It could be like a noisy matrix instead of a time aggregated one, and you can think about whether the model I'm about to introduce actually makes sense for your setting.
Thank you.
So you have this general network problem, and IPF poses an attractive method to use here because it also deals with marginals, right? But IPF has been mainly used in matrix balancing, where the goal is just to fit those marginals, but there's no explicit network that you're trying to infer underneath. And so the goal of this work for us was to answer this question, why is IPF a good idea here? And more specifically, under what generative model is IPF a reasonable estimator of a dynamic network from its marginals? I'll go over our result mainly, but happy to talk about the details. We answer this question by finding a generative network model where IPF in fact recovers the maximum likelihood estimates of the network's parameters. And so in our model, we have a time-varying network, which we'll call XT, and that's a scaled version of the time-aggregated network X bar, drawn from a Poisson distribution. And each entry is scaled by a parameter for the row, Ui, and a parameter for the column, Vj. And in this model, we're going to say we observe the time-aggregated network X bar, but we don't observe the time-varying network Xt, What we do observe are the marginals of the time-varying network, meaning the row sums and the column sums again, and we show, in fact, that these marginals form sufficient statistics for the model. And so based on that, our main result is that under this model, IPF recovers the MLE, the maximum likelihoods, of the scaling parameters U and V. And I'll skip the proof for now, but the basic idea is that the log likelihood of our model is actually equivalent to the KL divergence, the dual of the KL divergence problem implied by IPF. And I can point you to the proof if you're interested. But let's focus on the implications of this result. Why do we care? Well, first of all, we've answered the question, which is what is a model under which IPF is a reasonable estimator of a dynamic network from its marginals? And our model also reveals implicit assumptions that we're making about the network when we use IPF to infer it. So for example, we're assuming that there are only time-varying row and column factors, but there's no time-varying interactions. Our model also enables several new analyses of IPF. So for example, we can now evaluate IPF's estimation error on the true network parameters, and we have some both theory and empirics on that. Previously, people mostly evaluated IPF on its ability to match the marginals, but not on the true parameters. And you can also, for example, quantify uncertainty in IPF's parameter estimates and test IPF's performance under model with specification. And our paper also includes other results like an algorithm to enable IPF iterations to converge when they have trouble converging on sparse network data, as well as some empirics where we actually had the ground truth hourly networks using bike share data.
Why wouldn't the interactions show up in the time-varying row and column factors? So for instance, like congestion on the highway between a census block and a restaurant could be an interaction.
Yes.
But that would show up in the marginals, right?
Yeah,
the number of people getting to a restaurant at a certain time.
Yeah, so it's actually not that restrictive of a condition. Like having time-varying row and column factors gets you a long way. An example of where you might have a time-varying interaction would be the example we have in our paper is if you have some place, let's say a restaurant, that has special discounts for seniors on like Sundays, then you would have an interaction between neighborhoods that have a lot of seniors in them and that place on Sundays. Does that make sense? Yeah. Cool. So now we're going to come back to our original application, but again, happy to discuss the math a bit more later. We applied IPF to our hourly CBG POI networks, so now we can infer them for 10 of the largest metropolitan areas in the US, from March to May 2020 in the first wave of the pandemic. And I've talked a lot about the theoretical properties of IPF, but a nice practical property is that it's very lightweight, meaning that you can compute all of the row factors in parallel and all of the column factors in parallel. And so we're able to infer these large-scale networks with 500,000 POIs, 57,000 CBGs, and 5.4 billion hourly edges. And we've also released our networks in agreement with SafeGraph, which have been downloaded by hundreds of researchers and used in follow-on studies. If you're interested in looking at them, I can share them with you as well. But now we're going to integrate our mobility network into an epidemiological model. And we use a standard compartmental design, meaning that we assume that people can be in one of 4 disease states: susceptible, exposed, infectious, and removed. And the key to our model is that we maintain disease states for every CBG, for every neighborhood, and then the mobility network that we inferred governs how the CBGs come into contact with each other. So I'll go through a simple toy example to explain how the model works. Let's say we just have 2 CBGs, A and B, and everyone is susceptible for now, except for one person in CBG B who is infectious. And now let's say there's an infectious person and the susceptible person, they show up at the same POI. And now there's some chance that the infectious person infects the susceptible person. Let's assume, unfortunately, that happens. So now the susceptible person becomes exposed, meaning they are infected but not yet infectious. And then after some time, both people go home, and now the exposed person also moves on to infectious. So exposed means you've been infected, but you're not yet able to infect other people. And then we also model a second type of transmission that happens in your home CBG, and that's separate from POI visits. That's things like you share the same elevator with someone, or maybe you're actually in the same apartment. Let's say that happens here. So now we have 2 infected people in each CBG. So this was a simple example, but it can show you how the model combines the mobility networks with the disease states in order to model the spread of disease over multiple CBGs. We also model POI-specific probabilities of infection based on additional data that we have from SafeGraph. So for example, the POI's area in square feet, the median dwell time, We have the number of infectious visitors, which is endogenous to the model, and then also current levels of mask wearing, which are reported externally. And altogether, our work can be described by this pipeline. So first, we infer the mobility networks from the aggregated location data, and then the networks, along with many other ingredients, are put into the epidemiological model. And then we learn the free parameters of our model by fitting it to daily case counts, and then we use the fitted model to conduct various analyses. So incorporating so much real-world data means that, as promised at the beginning, our model can actually be very simple. Our model only has 3 free parameters fixed over time, literally 3 numbers. Despite that, we are able to fit all sorts of case curves during the first wave of the pandemic. So here the blue line represents our model predictions, and the orange line represents daily reported cases with weekly smoothing. And you can see that our simple model is able to fit linear trajectories, like in Chicago, but it can also fit harder curves, like cases that plateaued in Philadelphia, or even those that went downward. Certainly the fit's not perfect, but remember our model only has 3 parameters, and all of the time varyingness comes from the mobility networks themselves. So this shows the power of our mobility networks, since they enable our simple model to fit these complex case curves. And we conduct various robustness checks on model fitting. For example, we compared our model, which uses these IPF inferred networks, to an aggregate mobility model that still receives the total hourly mobility, but no network. So you're able to capture that there is a huge drop in mobility early in the pandemic, but you can't see who is going to where. And we show that our model with the network substantially outperforms the aggregate mobility model with a 42% decrease in RMSE, suggesting that these inferred hourly networks actually matter quite a bit. We also tried simulating disease spread with known parameters, and we showed that our model fitting procedure could recover the true parameters in all 10 metropolitan areas through the issue of identifiability. And then we also conducted a large number of sensitivity analyses, and to summarize the results, we found that none of these changes made a real difference. So now we have this working model. What can we use it for? First, we use it for retrospective analyses. So meaning our model can realistically simulate who got infected where and when, down to the individual CBG, POI, and hour. And so this allows us to analyze, say, disparities in risk, like which CBGs are getting more infected. It also allows us to analyze disparities on the POI side, in terms of risk, which POIs are riskiest to visit. And second, we can use the model for forward-facing experiments. Because our model takes in a series of interpretable inputs, like the networks or the initial disease states, you can modify any of those inputs and run the model forward to see how the predicted infections change. I'll give you an example of 2 use cases. One of them is around reopening. And so we studied reopening strategies with our model using the fact that we have these mobility patterns that we can tweak. And so we tested a partial reopening strategy where we reopened all POIs, but we capped visits for each POI to some percentage of its maximum occupancy. And then we evaluated each reopening strategy based on 2 objectives. So on one hand, we want more visits. That serves as a proxy for, say, the economy and consumer needs. But on the other hand, we want to minimize infections. And so what we find is, as expected, these are competing objectives. So more visits lead to more disease spread. But the exciting result is that the relationship is highly nonlinear, meaning that a small reduction in visits can get you a large reduction in infections. And the reason this strategy works so well is because it disproportionately reduces visits at POIs during their dense, risky hours, but otherwise it returns visits as usual to most POIs that aren't getting close to their maximum occupancy cap. So exploiting those heterogeneities can actually allow you to get better decision making. We can also use our model to analyze health disparities. And so it was well known by the time that we were releasing our model that there were large disparities in infection rates, with lower income and minority communities getting infected at higher rates. The question though was, where were those disparities coming from? And what was interesting for our model is we didn't tell the model the demographics of the CBGs. It didn't know which CBGs were lower income or more minority, but it still correctly predicted disparities in all 10 metropolitan areas, giving the more minority and the lower income CBGs more infections. So the question is, how is the model able to do that from the mobility networks alone? And we found that there were 2 reasons. First, lower income and less white CBGs weren't able to reduce their mobility as much. And this could be because they're disproportionately represented in essential jobs or less able to work from home. But it's not just how often people go out, it's also about where they go. And we found that people from lower income and less white CBGs tended to visit POIs that were smaller and more crowded with longer wait times, and therefore riskier under the model. For example, we found that one trip to the grocery store was 2 times riskier for someone from a lower income CBG compared to someone from a higher income CBG. So these findings reveal that mobility could be playing a substantial role in why we see these demographic disparities in infection rates, which then informs how policymakers should tackle these disparities. So when we released this work, we were excited that the findings reached broad audiences. We received coverage from over 650 news outlets, including an interactive article in the New York Times. Maybe more exciting was that our work was also cited by various institutions and governments around the world. For example, here you can actually see one of the figures from our paper remade by the Office of the Prime Minister in Poland. We are also cited in amicus briefs for the US Supreme Court and by the CDC and other institutions. But given all of this attention, we wanted to translate it into concrete decision support for policymakers. And so to do this, we partnered with researchers at the University of Virginia who are advising the Virginia Department of Health on pandemic policies. And they reached out to us about the department's need for data-driven tools to assess potential reopening plans. And so together, we transformed our model into a new dashboard that allowed the Virginia Department of Health to test thousands of different hypothetical mobility plans so that they could analyze trade-offs between predicted infections and mobility. And creating this dashboard required substantial effort, for example, new features, a computational infrastructure, and new visualizations based on our discussions with the department. And in recognition of our efforts, this paper actually won the Best Paper Award in KDD in the Applied Data Science track. So that concludes what I wanted to say about mobility networks and COVID. Briefly, let me say that I've also worked a lot with other data sources that you might have also worked with. To take a big picture view on these data sources, I think things like mobility data are really useful for telling you what people are doing, but it's not enough to just know what people are doing. It's also really valuable to understand what they're thinking and feeling. How do they actually arrive at those behaviors? So in other work, I've used data sources such as search log, speeches, and social media, more user-generated data, so that you can actually get at these sort of beliefs and motivations. Briefly, some of these papers include analyzing vaccine uptake and hesitancy from search logs, or measuring attitudes towards immigrants from 140 years of US political speeches, as well as some work, older work on social media. So to end this section, let me do a little bit of discussion on, of course, these data sources aren't perfect. Mobility data can't cover all populations, for example, seniors or people in prisons, which are populations of interest during pandemics. Search logs also don't cover all individuals or types of vaccine seeking, for example, walk-in appointments. And of course, privacy is also an important consideration at all times when using these sort of passive data sources. How do we balance social benefits along with privacy? The models, of course, are also imperfect. So SEIR, for example, makes simplifying assumptions about disease transmission. But that said, the behaviors that we can estimate are at much finer granularities, and they achieve strong performance, strong predictive performance, and they allow us to derive important policy insights. So I talked mostly about the first bullet point today, which is mobility data and the SEIR model. And now we have these hourly mobility networks that enable accurate fits of COVID cases with a very simple epidemiological model. And we can study who got infected where and when, which informs reopening and disparities. In work that I didn't discuss as much today, the search logs and vaccine work, we were able to actually get AUCs of above 0.9 in all 50 states of predicting vaccine intent. So basically when someone is trying to get the vaccine on search. And we also show strong correlations with county level and state level CDC rates. And using that, now we have fine-grained real-time monitoring of vaccine rates and concerns. And we actually show that our search signals precede the CDC by 1 to 2 weeks in terms of their reporting. So there's this gap between when somebody looks on search, where can I get a COVID vaccine, versus the delay for them to actually get vaccinated, and then that vaccination to get reported by the CDC. And so now you can actually preempt demand in a way. So that concludes my first part on inferring behaviors from novel data sources. We're going to now switch gears to simulating behaviors with LLMs. And I'll start with our recent work on generating social networks, and then I'll try to give you a bigger picture, depending on time, of my ongoing work in this area. So this is a paper, very recent. It's under review, and it's out on arXiv right now. It's co-led with Alicia Hashevich. And so this work is about generating social networks. which is important in many applications where you need a network, but you don't observe it. For example, we were just talking about epidemics. You might want to model spread over contact networks. Instead of inferring it, maybe you simulate it. Or you might want social networks to simulate social phenomena like polarization or opinion dynamics. Or maybe you're prototyping a new social media platform and you want to say, what is a realistic social network in this prototype? So classic approaches to generating networks include using stylized network models like Erdos-Renyi or small world models, but these models tend to be rigid in their hyperparameters and they're not very realistic. On the other side of the spectrum, we have deep learning approaches, which are more realistic, but they require a lot of data to train those models. So you take a bunch of observed networks and you fit, say, a graph neural network to that data, and now you can actually generate another social network, but they require a lot of data. So here, we're exploring LLMs as a promising new approach because, first of all, they're flexible. So you can describe any agent in your network using natural language, any demographics you want. You could even include different features for different agents. Second, they're zero-shot, meaning they don't require additional data to generate. And third, and this is the question, they could be realistic based on the fact that they've ingested a large amount of social knowledge during pre-training, but the question is, are they? And so the key question in our work is, can LLMs generate realistic social networks? And on one hand, this might be promising because, again, LLMs ingested a lot of social knowledge during pre-training. There's also prior work from John and others showing that LLMs produce human-like responses and interactions in experiments or simulated scenarios. On the other hand, though, it's not clear how LLMs' language abilities will generalize to discrete structures like graphs, and prior work has actually shown that LLMs struggle with reasoning over graphs, for example, finding Hamiltonian paths. Also, LLMs sometimes show demographic or political biases. Prior work has shown that as well. And this could be a particular issue for social network generation because demographics play such a central role in how we choose our friends. So we can't really get around the idea of not including demographics. So to answer this question, we designed 3 prompting methods for generating social networks with LLMs. First, we have what's called the global method, where we ask the LLM to generate the entire graph at once, based on their descriptions. In the local method, we have the LLM take on the identity of one persona at a time and have it choose edges for that persona based on descriptions of the others. And then finally, in the sequential method, it's quite similar to the local method in that the LLM again takes on the identity of one persona at a time, but in addition to seeing descriptions, it can also see the network as it was generated so far. So we can actually take into account this network information. And then in our experiments, what we do is we sample the persona demographics based on the real US population distribution. We generate 30 networks for each method. To evaluate the networks that are generated, first we look at structural characteristics of the networks. So things like density or average clustering coefficient or community structure. And then we also look at homophily, which is, you probably know, our tendency to become friends with people who are similar to us. And in this work, we measure homophily as the ratio of observed same group edges, so that would be like same gender or something, divided by expected same group edges based on the proportions of the populations. And then finally, we compare to 8 real-world social networks that include students, physicians, also the famous karate club network. Our first result is that local and sequential generate much more realistic networks than the global method. So that is, the LLM struggles when we ask it to generate the entire network at once, but it does a lot better if we ask it to take on the identity of one persona at a time. So in these plots on the left, I'm showing you, or on the right for you, I'm showing you the mean and standard deviation over networks for each characteristic, and then we also visualize individual networks as dots to show individual level variability. And you can see that the LLM, the local and sequential methods approximately match the means of each structural characteristic, while global is quite off. And this is interesting because it aligns more with how we make friends in the real world. Most people don't enter a network with a complete global view of everyone who's friends with whom, and then you say, I want to enter that part of the network. It's much more local, right? You are one persona, and you have some local view of who is friends with whom within your circle, and you choose friends that way. And it's interesting that in that local view, you still see these consistent global patterns emerge.
One thing I'm curious about, since you brought up kind of aspects of realism,
Yeah.
Are there any constraints on like connection or friendship formation here? Because, for example,
Yeah.
like humans have capacity constraints. I
Yeah.
don't want like an infinite Rolodex. but an
Yeah.
LLM might not have that, and like the
Yeah.
way that the prompt was phrased,
Yeah.
kind of seemed more like a threshold. Like, is there enough
Yeah.
affinity between these two agents to be friends?
We're trying to keep it as light-handed as possible here, like really zero shot.
Yeah.
And so we don't include any sort of restriction on how many people can be chosen. Like the prompt is literally just which of these people will you become friends with. And we do experiment also with saying the number, but it doesn't seem necessary for local and sequential to get the right density.
Interesting.
Yeah.
I was curious about like how robust are these things to the prompt? So like something I've noticed when using LLMs is, for instance, if it spits out a response and I say, are you sure about that? Sometimes it'll bend over backwards to give you a different response.
Yeah.
So like with that kind of thing, I could imagine like you tell like, oh, who would you make friends with? And then if I were to enter another prompt, like, are you sure you'd be friends with that person? It would give me something different.
Yeah.
So have you tested that kind of robustness?
I'll talk briefly about sensitivity analyses at the end, but yeah, it's a good question. Let me go through our remaining main results first. So we also can compare the local and sequential. Remember, in both of these, we assign the LLM the persona one at a time, but the difference is that in sequential, we also show it the network as it's getting generated. And the resulting difference is that sequential is able to match the degree distribution better than local can. So local doesn't get the long tail degree distribution, while sequential can. And sequential is also able to simultaneously match these 6 essential characteristics of social networks, which we show is a non-trivial fact. And so, for example, classical network models are not able to match all of them at the same time. Our other set of results are around homophily. And so this is a tendency to become friends who are similar to you. And our measure of homophily, remember, is this ratio of observed to expected same group relations. So a ratio above 1 indicates homophily. You can see here that across all 3 methods and across demographics, the LLMs clearly capture homophily. What's interesting, though, is that the LLM tends to put the most emphasis on political homophily, especially for these more realistic local and sequential methods. For example, under local, same-party relations are 85% more likely than expected. Under sequential, they're 68% more likely. We also find that political homophily remains the strongest even if you shuffle the demographics. The reason to do that is to break correlations between the demographics. Homophily and political is still the strongest. You might also think that the LLM is paying too much attention to demographics because we didn't provide any other information. So we try including interests as well, generated by the LLM, and we find that that doesn't change the situation. Partially, that is because the LLM-generated interests themselves encode a strong level of political homophily. And so, for example, I think like 60% of Democrats like social justice. And so that also contributes. And so you could think about maybe instead I want to handcraft these interests, and that would definitely be interesting to explore. But for large social networks with 50 to hundreds of people, you might not want to be doing that. And so maybe figure out other ways of generating interest that are less biased. Our final result is that it's not only that they put the most emphasis on political homophily, but that it's actually being overestimated. And we compare to real-world measures of homophily across both offline and online networks, online being Twitter, offline being things like family or work or people that you would talk to about politics. And our LLM's measures are still above that across all networks.
Did you compare this approach with sort of like kind of a naive non-LLM approach? I can kind of see that like what the methodology here for the LLM where it's contributing is it's basically like looking at like a possible edge formation and then like you feed it some like information about the features in each node and you're basically trying to say, hey, is there a matching here? You can imagine like a more simplistic method where it's just like literally running a logistic regression on like certain features like, you know, based on your demographic. And like have you kind of compared like sort of the LLM approach, like when it's buying you on top of like sort of a more feature-based approach like that?
But in your feature-based approach, like logistic regression, what would you actually be training your logistic regression model on?
You sort of have the existing networks already, right? Or like you have existing networks that kind of suggest like demographic, sorry, I don't know the granularity of the social network, but I'm just wondering if there's like some kind of testing.
So I think in the logistic regression approach, yes, you do have existing networks, but the hope here is to be able to do it in a zero-shot setting where you don't need any networks to train on in order to be able to generate the networks. So that's part of the value of the LLM, where you can take completely hypothetical agents in completely hypothetical situations and try to generate networks between them. For the logistic regression, you could fit it on, for example, the 8 networks that we do have here, but then you'd have to fit it on networks.
I see, because you're not assuming you're given like the feature, like the nodes with the features. Okay.
We're assuming you're not given networks. Okay, and so some additional results. We tried 6 different models to GPT models, to Llama models, to Gemma models. The results I told you about are from GPT 3.5 Turbo, since it did the best on the structural characteristics. But we do find that all models overestimate political homophily, and in fact, it's most extreme for GPT 4.0 and Llama 3.1 70 billion. Kind of interesting, because those are the most sophisticated models here. And most extreme to the extent that they completely refuse to make Democrats and Republicans friends, and the network fractures into two disconnected components, which is not supposed to happen. Yeah.
Do you think it's like an RHLF thing? Like that
Yeah.
like the other dimensions is probably, it wouldn't be okay to say, I don't like Hindus.
Yeah.
But it's probably okay to say, I don't like Republicans.
Maybe, yeah, it's a good question. I mean, we should compare fine-tuned versus base models that haven't been fine-tuned on our RLHF. I think the other possibility is that it's just seen a lot of discussion about polarization online, and so it overestimates even compared to online networks. Yeah, I think someone could write a whole other paper like, why is this happening, now that we've documented it. Yeah. Yeah, and then we also tried a number of other things. For example, you can ask the LLM to give you a reason when it chooses a friend. We also see that the political thing is happening there. It gets mentioned 87% of the time. The next most common demographic to be mentioned is religion, which is 43% of the time. We also look at the LLM-generated interests a bit to evaluate bias in it. And then to your earlier question on the robustness to different sensitivities, we do try varying the temperature. We also try minor changes to the prompt. So instead of asking how many friends, we ask it slightly differently, or with or without asking it to generate the reason, it still produces qualitatively the same results. Great, okay. With a bit of remaining time, I'll zoom out and tell you about my ongoing work on simulation, but I'll try to do that in 5 or fewer minutes. I'm interested in simulation across scales, from individual responses to interactions between people to human AI interactions. So one project that we're working on right now with some students at Berkeley is simulating public opinions. And so the way that this is often done is you prompt the LLM with some sort of public opinions questions, like gun control, then you extract the LLM's log probabilities for each answer option, and you compare it to the ground truth distribution from the US population. This figure is taken by Sandra Kerr et al., not a paper that I'm on, but they set up this framework very nicely and set up a data set for you to compare against. And so one of the findings from this paper is that if you ask the LLM without specifying any demographic group, the LLMs will tend to skew their answers towards more liberal, more educated, and wealthy people. People also think RLHF could be a reason for that because of who's doing that labeling. But the interesting thing is, even if you try to steer the LLM, so meaning you actually specify which demographic group it's supposed to be emulating, the LLM, that doesn't fix the problem. It helps to close the gaps a little bit, but there's still substantial gaps between the LLM distribution and the human distribution, even with that steering. And so our goal in this work is to come up with better steering methods to make LLMs more steerable. Most steering methods have been prompt-based. Our theory is that prompting is not enough. And so we're trying to develop fine-tuning techniques that will teach the LLM to be more steerable. We have some preliminary results right now where we find that if you fine-tune on a subset of questions, let's call that Q-train, we not only see improvements on those questions, but we also see them on unseen test questions, Q-test. And so then the question is, why is that happening? We're trying to disentangle 2 hypotheses. One hypothesis could be maybe the test questions are easily predictable from the train questions, since we know that public opinions are very correlated. Maybe we see gun control in train and abortion in test, and it's easy to predict one from the other. The other interesting hypothesis, though, and this is inspired by the Lima paper, for those of you who know it, is that the LLM actually knew the test opinions all along. It knew it during its pre-training. And the point of fine-tuning is to teach the LLM to retrieve those opinions correctly and to format them in the expected way when they come out. And so I think answering this question is really important for understanding how these simulators can be used and how far you can generalize after fine-tuning. And the final work I'll tell you about is ongoing work that I'm doing on the human AI interaction side with some great people at Microsoft Research. And the premise for this work is that current AI evaluation misses how users are actually using generative AI systems. So for example, for question answering, the standard way, the way that existing benchmarks are answering this is with a question and an answer, sometimes in multiple choice format. And this is an example taken from MMLU, which was then used in Helm, which is one of the state-of-the-art benchmarks right now for evaluating language models. And there's several issues with evaluations like this. First of all, they're static, just a single question and an answer. It's not interactive or multi-turn, the way that people actually talk to these models. Second, to evaluate these models more easily, it's often multiple choice instead of open-ended. And other issues are that the topics of these questions might not match what real users are actually interested in, and the style of asking the question could be different as well. And so what should we do instead of these static benchmarks? Ideally, what we'd have are infinite copies of real users for evaluation. Every time you want to evaluate a set of systems, you get all of those users, you have them start the same conversations with all of the systems, and so you can evaluate the full counterfactual. This is not possible. Even for places like Microsoft, people don't have this sort of infinite access to users. So instead, can we realistically simulate users as proxies so that we can better evaluate these systems? And so the goals of our project are, well, first of all, we want to develop a simulator that closely matches how real users interact with generative AI systems. And since we're at Microsoft, we have a chance to actually compare our simulator to real users of, say, Bing Copilot. But our second goal is to then take the simulator and design interactive evaluations, for example, for question answering, but for other tasks as well. And there are two sub-goals here that I'm quite interested in. One of them is, once we have this interactive evaluation, how do evaluation conclusions change relative to static benchmarks? Do we see a reordering of the ranking? Do models seem to perform better or worse? A second question is, the goal of evaluation is often to estimate some target parameter, like question answering accuracy or the prevalence of harms. And so that's actually what you're trying to do when you use a simulator. The idea is if you replace human conversations with simulated conversations, how well can you estimate that original target parameter? So the goal now no longer is, let me make the most realistic simulator as possible. The goal is, let me try to estimate my target parameter as accurately as possible. And those two goals are related, but they're not exactly the same. And it's interesting to think about how they're connected to each other. And finally, I think I would say about my ongoing work about simulation, an overarching theme is how do we make LLM simulation useful in the real world? I think there's been a really exciting first wave of LLM simulation where people tried all sorts of scenarios and they're like, look, we can kind of do this. And people are like, yeah, that's cool. And now it's like, how do we actually make it useful? And I think in making it useful, there's a couple of questions to ask. How do we properly validate these systems and document gaps between humans and LLMs? Second, when we do see these gaps, how do we close these gaps? For example, with the fine-tuning methods. But the third thing, which I might actually be the most excited about, is how do we actually integrate simulators into downstream pipelines, like AI evaluation, like survey studies. And when we do that, that's going to reveal really interesting research questions around, for example, what does a simulator need to get right in order to be useful? So I'm going to conclude my talk with that, and thank you so much for listening.
A question about this idea of steerability and in regards to the homophily.
Yeah.
So in a sense, we were talking about like, can you unlearn some of the biases, right?
Yeah.
From the LLM. So would you be able to, for example, introduce a new training data set or a RAG approach where you have documents about maybe the complete opposite of like, making friends with like very disconnected or dissimilar people, and would that then therefore bake in a level of like opposite,
I think, that could be one approach. I think of giving it data where you show, like Democrats and Republicans are actually friends sometimes, and you like fine tune it maybe on those data sets, and then it can kind of unlearn those biases. It'd be interesting if there's like also ways, prompting-based ways, of maybe around reasoning or around something. I don't know. Yeah, I think that is promising. For steerability in our public opinions project, we're actually thinking about something like RAG, where you retrieve, like the data set that you're retrieving from is the demographics past opinions. Because the whole idea of fine-tuning is you have Q-train, right? You have some database that you do have access to, where for those questions, you know the demographics answers to those questions. So instead of just like doing vanilla fine-tuning on those questions, could you actually use those questions as in-context examples? And then it can reason about the answers to those questions when it's doing like a new question. So I think that could also.
And is there any way for you to sort of obtain the opinions of folks who do RLHF so that could actually explain a lot of like this liberal bias?
Yeah, it's a good question. I mean, I don't know. Maybe if people know if there are data sets on that, we would be very interested.
You'll sign up for Scale AI.
Yeah.
As an employee at Scale AI, yeah.
Right. I think that would be interesting.
Okay, anyone have another question? We got 2 more minutes. John.
I wonder if in say like the friendship formation, it would be interesting to try to more like micro model how people
Yes.
form friendships.
Yes.
Like, hey, you're all gonna go to this, you are your coworkers,
Yeah.
or this is your college roommate or whatever.
Totally.
Rather than, like here's the set of potential friends you
Yes.
can choose from.
Yeah, I mean, that's actually one of the first like future directions that we've identified, which is like the way that we're asking the LLM right now is sort of contrived. It's just like, here's a list of people, who are you friends with? Maybe that matches Facebook or something, but it's not the way most people make friends. Like we want to explore this more organic version of friendship where you maybe create all of these LLM agents that all have personas, you throw them in some simulated world and you have them talk to each other, and then you see organically what sort of networks arise from that.
Have you seen the party model, the Jackson party model, where they go to a party and they have a limited amount of time?
Oh no, I don't think so. I was thinking more of like June Park's work at, they have like social simulacra and generative agents, so I've been talking to June about possibly like organic networks that way. But what is the party
Matt
model?
Jackson.
Okay, okay, I'll look into that.
There's an AER paper and a PNAS paper that describes this.
Oh,
Nice.
how people make friends. Yeah.
It's like they all get thrown into a party and there's
Yeah, they're
limited
all at a
time.
party.
And
It's
stuff.
like a mixture.
That's funny, I like it.
I was also thinking, like, just based on what you said, like maybe there's some effect where like the researcher's trial could influence results because it influences the way I write that prompt. So maybe like there's features of the setup which as a researcher I don't think that's important. So I never specify in the prompt and then hey, the results show that's not important because I never included it in the setup. And like, is that a thing you're worried about?
I think it's a good question, and I think as in general, that's like a concern about agent-based modeling, which is you sort of get out what you put in. I think LLMs actually have an advantage in that sense, where it's like a black box and you just say like the most vanilla prompt possible. Of course, there is still, you still have degrees of freedom in what prompt you write. We try to keep the prompt like as light-handed as possible. And so we really just, of course, by including these demographics, we're implying that these demographics should matter. We don't tell it which demographics should matter more or less. We don't tell it how many people it should be choosing. We randomize the ordering of the people who are going into the prompt. We randomize the ordering of the demographics and so on. But yeah, I think it is something to be really careful about.
It kind of seems like they almost have this like Chekhov's gun principle. Like if you mention it, it has to be used in the answer. And so like what you choose to kind of create as their background ends up having a lot of influence.
Yeah, so I think it's more fair to compare like within the things that you mention, what gets paid more or less attention to. So we can see, for example, varying levels of homophily over the demographics that we did mention. But it's harder to say like, we didn't mention some other kind of demographic and it didn't pay attention to it as expected.
Actually, would you get anything where it's like you mention something in the prompt but it just doesn't use it at all?
Doesn't use it at all. I mean, I think the closest I can show you is like homophily that is lower. So I think, let me see, what was the lowest form of homophily? Like, yeah, so like if you look at local and sequential, like gender is only 20% above expected, whereas political is like 85% above expected. So I think you can really compare within.
So one thing I've seen in experiments with like LLM-based agents is there does seem to be a slight difference in behavior if the situation is framed as first person versus third person. Have you thought about that in the context of like different results that you've shown here?
We tried that in our early experiments. I don't think those results are actually recorded in the paper. It's a good reminder that we should have them. But we did try them when we were trying out the prompts initially, and it didn't make a difference.
How about for the like the survey?
So there we try, and this is from the original Santa Car paper. They have 3 different types of steerability, like 3 different ways of describing what demographic you are. They have one called QA, which is basically in the multiple choice format. It's like you ask the question like, let's say the question is about race, and it's like, which racial group do you identify with? And then the options are like A, white, B, black, C, Asian, whatever. And then you write the answer like B, black, and like that's part of the prompt. And that's pre-pended to the actual public opinions question you're asking. That's QA. Bio is another one where it's like formed as a bio, so it's like answer as if you are this group. And so yeah, I think that's sort of, we do see slightly different results across different steerability methods, and that is important to look at.
I have a question on the ongoing work. So my understanding was that the goal was to use LLM to generate sequence of that interactions and use that as new benchmarks for future LLMs.
This is for the user simulation?
Yeah.
Okay.
Is that like the correct focus? Because I was thinking, because generally there's this premise like, you don't want your training data to be, or you don't want like your test data to somehow, be represented in your training data, right?
Yeah.
But then this sort of work, it feels like the LLM that you're gonna evaluate on will probably be trained on some interaction data that this agent, this generator also seen. Like how does that come into
Yeah, I
play?
think you'll want to split things carefully.
Mhm.
So for example, let's think about like the question answering
Yeah.
setting. So now you have some set of questions, you have some set of answers, and what we're thinking about doing is actually like running a user study where we take users and we seed the user with the question. So we're like, you are a user who wants to answer this question. We have them talk to the LLM to try to answer the question. And now for every question in the original static benchmark, we have like a conversational version of it where the user was seeded with that intent. So now we create some sort of data set, and then to actually test the simulator, you could do the zero-shot version, where zero-shot doesn't have to worry about leakage too much. But if you do want to actually fine-tune the simulator on your newly constructed data set, you'll have to split the data carefully. And so maybe you can split it on the question level, and so you've trained it on certain questions, where now the simulator has learned how to act like a user when asking a question, but now you test it on unseen questions entirely. You could even try to test it on unseen systems, where it's like you were training it on conversations with ChatGPT 3.5, and then you see whether it can generalize to GPT 4.0.
Oh, okay.
Or something. So you just have to split it carefully.
Okay, thank you.
Yeah.
Well, I think that's the time.